Okay, in this section 13-2, we're talking about compound probability. And so in the last section, we just talked about a single probability. So now we're talking about compound probability, which is the probability of more than one event happening. So just to review, remember, probability is favorable over total, meaning what you want over the total number of possibilities. Now, the probability of two independent events happening. All right, so the probability of A and B happening would be the probability of A times the probability of B. So last time we learned how to do individual probabilities. So this time you would do the same thing, the probability of each individual event, but the probability of both of them happening would be those individual events times each other. All right? Now, that's if they're independent, like one doesn't depend on the other, right? Or the outcome of one does not have any effect on the other, I should say. Now, the probability of two dependent events happening would be the probability of event A happening times the probability of event B after event A has happened. Because two dependent events would mean that that event A happening would have an effect on event B. Okay, so if they're independent, they don't have any effect on each other whatsoever. But if they are dependent, then event A happening is going to change the probability of event B happening, right? And you'll see the examples of when that occurs when we get to it. But remember, if they're dependent on each other, then it's the probability of event A times the probability of event B after A has already occurred. All right, so indicating there would be a change in probability once that first event A has happened. All right, so when we go and take a look at each scenario, we've got to decide, first of all, are they independent events? They don't have anything to do with each other, or are they dependent events? One happening affects the other. All right, here's the first example. Rolling tails on a coin, or flipping tails on a coin, and then rolling an even number on a die. All right, so first of all, let's decide whether these are independent or dependent events. So does flipping the coin have any effect on the dice at all? The answer is no, it doesn't. They're two independent events. So all I have to do is find the probability of one, the probability of the other, and multiply them together. So what's the probability of getting tails on a coin? Well, what's the favorable amount? How many tails are there? There's one. How many total outcomes are on the coin? 2. The probability of getting tails is 1/2. It's going to be times the probability of getting an even number on the dice. How many even numbers on the dice? Well, there would be 3 of them, 2, 4, and 6. How many total numbers on the dice? 6. 3 out of 6. Okay? You can either reduce that now or later. If you multiply them first, you would get 3 over 12, which then would have to be reduced to 1/4. So the probability of getting tails on a coin and an even number on the dice at the same time, 1 out of 4. All right? Two independent events, the probability of each one, multiply them together. Okay, now here's a different scenario. Let's say that we've got a box with 4 green, and it can be whatever you want, chips, green objects, whatever the object happens to be. 4 green objects, 3 red objects, 3 blue objects. All right? We're picking 2 without replacement. We want to find the probability of getting a green one on the first try and a blue one on the second try. Okay? Now, a couple of things to consider here. Number one, we're picking 2 without replacement. So we'll pick one, then we'll pick the other one. Okay? Now, since this is without replacement, these are dependent events because the first pick changes the probability of the second pick because it's without replacement. So 3, 3, and 4, there are 10 objects in the box. After the first pick, there are no longer 10 objects in the box. There would be 9. That affects the probability. All right? So these are dependent events, right? Dependent events, and we have to treat them as such when we're finding the individual probabilities. Well, first of all, I need to find the probability of pulling your green one. Well, on the first pick, we've got a full box. So there's 4 green ones out of 10. That's 4 out of 10. All right? Times. Now, on the second pick, I'm trying to get a blue one. Well, how many blue ones are in there? Well, did we pick a blue one on the first pick? No, we did not. So there's still 3 in there. Right? Now, is there still 10 in the box? No, because we pulled one out. The key word is without replacement. And so this would be a 9 for the total amount on the bottom one. So you can see how, since they are dependent events, it affects the probability of that second pick, right? So when I multiply, I'll get 12 over 90. And this, again, now will need to be reduced by 6 to 2 over 15. So I have a 2 out of 15 chance of picking a green object on the first pick and a blue object on the second pick. Once again, that's without replacement. Another thing to consider would be this. What if it said pick a blue one on the first one and a blue one on the second one? Well, the blue one would be 3 out of 10 for the first one, but it would only be 2 out of 9 for the second one, because we already pulled one out, and the one that we pulled out was a blue one. So there would no longer be 3 blues in there, there would be 2. So without replacement, you just drop the bottom number. Unless it's the same color, you would drop the top and the bottom number by 1. All right, so keep that in mind. Let me see. Okay, another common probability question would be questions about cards. And so in order to answer these questions, you have to know what a deck of cards contains. And I find nowadays even more, a lot of people don't know how many of each card are in there. So we got to talk about that a little bit in order to even answer those probability questions. Well, first of all, in a deck of cards, all right, you've got 4 different types or 4 different suits of cards. Okay, you've got diamonds, you've got hearts, you've got clubs, and you've got spades. Those are 4 different suits, 4 different types of cards. Now, for each one of those types, okay, you've got cards that are 2 through 10. Then you've got Jack, Queen, King, and Ace. And so I've got that all written out for you here. All right. So then what that means is 2 through 10. All right. That's 9 cards. 10, 11, 12, 13 with King, Queen, Jack, Queen, King, and Ace. So that means each one of these types of cards, there are 13. There's 13 diamonds. There's 13 hearts. There's 13 clubs. There's 13 spades. Right? Okay? And out of each individual card, like a 2, well, there's 4 of each one of these, because there's a 2 of diamonds, a 2 of hearts, a 2 of clubs, a 2 of spades, a king of diamonds, a king of hearts, a king of clubs, king of spades, ace of diamonds, ace of hearts, ace of clubs, ace of spades. So remember, there's 13 diamonds, there's 13 hearts, there's 13 clubs, there's 13 spades, but there's 4 aces, there's 4 kings, there's 4 queens, there's 4 tens, there's 4 fives, there's 4 threes, and so on. And that makes a total of 52 cards. All right? So now that we know that the numbers are, we can actually answer probability questions about them. All right? So let's say we have a question like this, where it says 2 cards are chosen with replacement. That means you put them back first. Find the probability that the first card is a club and the second card is a diamond. All right? So let's go for the first probability first. And this is with replacement, so these are independent events. Since we're putting the first card back before we choose the second card, the first pick doesn't affect the second probability at all. All right? So what's the probability that the first card is a club? Well, how many clubs do you have? You've got 13. So it would be 13 out of 52 times, now we put that card back, so we're back to a full deck, and the second card is a diamond. Well, since we put the card back, how many diamonds? 13. And how many total cards? Still 52, because we put it back. We didn't leave it off. All right? So I need to multiply these two together and reduce it. That would be 169 over 2704. And once I reduce that down, that will be 1/16. I've got a 1 out of 16 shot of getting those picks. All right? What about this one? 2 cards chosen without replacement. So this is dependent events this time. We're doing without replacement. Find the probability that the first card is a queen and the second card is an ace. First card is a queen. Well, how many queens you got in there? There's 4. So that would be 4 out of 52. Okay. Times. All right. 4 out of 52 times. So we're without replacement, and the second card is an ace. All right, so we pulled a queen out first, so how many aces are left? Still 4. But now there's not 52 in the deck anymore, there's only 51 cards in the deck. Okay? And so that would be, because I pulled one out and left it out. This is what? Keyword without replacement. Okay? So that would be 16 over 52 times 51 is 2652. And when you get these big numbers, I would suggest going to an online fraction reducer. It will save you a lot of time. When you try to reduce that fraction, you will see that it's 4 over 663 is the chances of choosing a queen on the first pick and an ace on the second pick without replacement. Now, if you wanted to get a better idea of that number, you could turn it into a decimal and then make it a percent so you can see what your percent chance of getting it is. Sometimes that expressing it that way is more applicable to getting an idea of what the real probability is, because 4 over 663, most people can't really visualize how good or bad of a chance that is. All right? 2 cards chosen without replacement. Find the probability that both cards are aces. Well, on the first pick, I have 4 out of 52. Now on the second pick, this is without, we're not putting it back, it's dependent events. How many aces are now left in the stack for the second pick? Well, remember, you picked an ace out on the first one, so there's not 4 left, there's only 3. And since we left it out, there's not 52 left to choose from, it's 51. Remember, it's always favorable over total. What you want, there's only 3 aces left. How many left? Only 51. That is 12 over 2652. We can reduce that down to 1 out of 221. All right? 1 out of a 221 chance that if you're dealt 2 cards, that both of them would be aces, provided that they're the first 2 cards that come off of the deck. All right? So that's an example of how you can kind of get independent and dependent probabilities.